A warm good morning to one and all who are participating in this 2 days online workshop. And today is the second day. And in the morning session of this day, we are going to see some of the basics that relates to the artificial neural network. And subsequently, in the afternoon session, we are going to see how to solve a problem or how to work out a problem in ANN using MATLAB environment. So what is this artificial neural network means? So we are going to mimic or we are going to artificially represent the neural network of our human brains, the network system of your human brain. Since this is man-made, we are going to call it by the term artificial. So this artificial neural network is generally called as ANN approach or ANN technique. So the purpose of this artificial neural network is to predict the outputs based on the inputs that we are going to provide. So initially, the network model that we are going to develop should be trained with the inputs and the subsequent outputs. And afterwards, it will get trained by itself so that prediction is possible. So with this introduction, we'll move on. So what a biological neural network is? So the purpose of this ANN is to develop a computing model. In order to carry out various engineering tasks for the purpose of predicting some engineering terms that is inspired by the performance and structure of our biological neural networks. Our neural networks are comprised of neurons. So this structure and performance of our human brain is being considered for developing a computer-based model. But the models, the artificially human-made models, they does not reach near the performance of the biological system, because the human brain is a superior supercomputer. So the artificial neural networks, that is ANN, that we are going to develop, whose performance cannot be compared with that of the human brains, because it is very impossible to simulate the number of neurons and interconnections that exist in a biological neural network. If I am going to consider a biological neural network, that is our brain, we have many number of neurons. We have 10 to the power 11 neurons and their interconnections. How these neurons are interconnected with each other so that the data are going to get transferred or processed. Secondly, the operations of the biological neurons is naturally asynchronous in nature. So what is meant by asynchronous? So asynchronous is nothing but executing multiple tasks at a time. So simultaneously, I am going to perform some multiple tasks. A human, we can do multiple tasks at the same time. We can eat at the same time, we can watch TV, we can speak with our mobile phones, or some other thinking we will be having. So multiple tasks that can be carried out by this our human brain networks. So because of this only, the performance of the artificial models cannot be nearer to the biological neural networks. So what are the features these biological neural network generally has? They are robust and fault tolerance. For example, when with the age, the decay of nerve cells takes place, but a significant difference in performance cannot be studied. So there will not be any significant difference in the performance, even though because of some age-related factors or some other factors, even when there is a nerve cell decay. But in the case of artificial neural networks, if there is any system-related degradation, obviously the performance level will get decreased out. The second one is the flexibility. We normally adjust to a new environment more rapidly without any programs. So that is in our system. So these biological networks automatically adjust to whatever new environment it is supposed to have. So without any programs or pre-programmed. But in the case of a robot that uses a ANN, but nowadays they are going with the multiple algorithms. But generally, as human, we cannot have a robot or a neural networks because it cannot automatically adjust to a new environment. If there is any pre-programmed instructions, then it can adapt. So the main advantage with the biological neuron is it can deal with variety of data situations. The data can be a fuzzy, that is which lacks in clarity, but the machines accept only zeros and ones. But even though the information that is available is fuzzy, that is in clarity, that can also be dealt with in the case of biological neurons. Or if the data is probabilistic in nature, or it is noisy in nature, or if it is inconsistent, then also the biological neurons can deal with the available data. But in the case of artificial neural network, it is highly impossible, or we have to change this into a definite information. Then only it can be processed. Then these biological neurons have collective computations, that is asynchronous mode, that is doing multiple tasks at the same time. So these networks, biological networks, routinely perform many operations in parallel and also gives tasks in distributed manner. Okay, so that is the main advantages or features of the biological neural networks and how this ANN is set besides that is seen. Then what is the structure of a human brain? So the human brain consists of a large number, so more than a billion of neural cells that process the informations. The informations can be obtained from the environment where we are going to live. Okay, based on that informations, the brain is going to process that with the use of higher amount of neurons that is present in our brain. So each neurons is a simple processor, and the interaction that exists between these cells makes the parallel processing possible. Okay, the interactions, how these cells are combined, how these cells are interacted with or interlinked with each other. So based on that, the parallel processing is possible. So what is a neuron? A neuron consists of a core. It consists of a dendrite for incoming information and an axon with the dendrites for outgoing information. A neuron is a core. It gets the information from somewhere, it processes it and it produces the output, and that is also processed or transferred to the subsequent neurons. So from neuron to neuron, the transformation or transfer of data or information takes place. So sure you can see. So neurons, we have a dendrites. The dendrites are nothing but sure the dendrites is specifically useful for getting the incoming information, whereas the axon with the dendrites is for outgoing. So here you can see the dendrites which brings the information from the previous neuron to the present neuron. Then we have the cell body, nucleus, and then we have the axon. From the axon, we are going to get it connected to the dendrites of the next neuron. Okay, so dendrites provides us the incoming information, the nucleus processes it, and the output will be provided to the axons. So the axons will provide the data to the subsequent dendrites of the next neurons. Okay, here these dendrites are connected to the nucleus or neurons by means of synapse. So here we have some terms, the soma or cell body. So it is nothing but where the cell nucleus is located. Here you can see the cell body. So it is where the nucleus is present. So dendrites are nothing but the nerves that is connected to the cell body, and the axons carries the impulses of the neurons. The impulses is nothing but the data or information through electrical signals. Through electrical signals, these provides or transmits the data from one neuron to the another neurons. The electrical impulse travels along an axon. So this triggers the nerve ending of a neuron to release chemical messengers that is called as neurotransmitters. So depending upon the amount of electrical impulse that a axon carries. Axon is nothing but the output of a nucleus or a cell body. The output of a neuron is the axon. So this triggers a chemical called as neurotransmitters. So when two neurons meet, that is the axon of one neuron get it connected to the dendrites, there is a small gap that is called as synapse. So these chemicals diffuse across this gap and bind with the receptor molecules of the next neurons, so that the data will get transferred from one neuron to the another. So depending upon the amount of electrical impulse, the neurotransmitters will be a chemical. The neurotransmitters will be developed, and that chemicals will diffuse into the synapse, which bind the receptor molecules to the next neurons. So the binding of this neurotransmitter, the neurotransmitter is nothing but the chemical, okay, to the receptor stimulates the second neuron. So the second neuron obtains its data or the input data through the electrical impulse from the previous axons. The electrical impulse triggers the neurotransmitters. So by the amount of neurotransmitters, the strength of the electrical impulse will be determined. So information is transported between the neurons in the form of electrical simulations along the dendrites. The dendrites is nothing but the communication that exists between the one neuron and the other neuron. So through electrical simulations only, the data will be getting transferred. The incoming information from the nearby neurons, we are not going to speak about only one-to-one neurons. There may be many neurons that may be connected with each and every neurons. So the incoming neurons from the neurons dendrites from various nearby neurons is added up and then delivered along with the neuron axon to the dendrites. So when these data will be passed away, when these neurons, the data that is present in the electrical impulse will be passed away. The data that is present in this electrical impulse will be transferred only when the electrical stimulation exceeds a certain threshold. Okay, this threshold is nothing but a maximum or a minimum value which is considered as a reference. Once that reference value is reached, then only the information will be passed or the neuron gets activated. If the values is lower than if the values is lower than the threshold value, then the neuron is said to be inhibited because the information will not be transported because it is lower than that of the threshold value. So a neuron gets activated only the incoming stimulation is greater than the threshold value. If it is less than, then it will not getting activated. So the connections that exist between the neurons are adaptive in nature. So what is meant by adaptive? It changes according to the information that is being received. So the connections that exist between the neurons in the brain are adaptive, that the connection structure changes dynamically. So we cannot predict what type of structure that it is going to have. It depends upon the complexity of the process or procedure. So these neurons are adaptive. That's the main thing or the main advantage or main features of these brain networks. It is adaptive in nature. So how we are going to relate these two things, that is the biological neuron and the artificial neurons. So based on this adaptiveness or changing dynability, the learning ability of the human brain is based. So how we adapt to things, how we perceive things. So that's why the IQ level changes from one person to another person. So how adaptive we are, how dynamically our network is changing. Okay, depending upon that only the learning ability of human brain changes. Now here we are going to compare the biological neuron with the artificial neurons. Okay, the dendrites provides the input information. So I am going to have the input 1, input 2 and input 3 which resembles the dendrites. The nucleus and the cell body is the structure that we are going to have, okay, which is based on a function. That are all things we'll see in the subsequent slides. Okay, that is a network. Then we have the axons. So the axons provides the output. Depending upon the electrical impulse, it stimulates the neurotransmitters. Okay, so that is my output. Then we have the axon terminals. So these outputs will be a input to other networks also. So this is how we are going to relate this biological neurons with the artificial neurons. Now, how this artificial neuron performance or artificial neural network performance is compared with the biological neural networks. So we are going to compare here some of the performance attributes. The first one is the speed. So in most of the advanced computers, the cycle time will be in the range of few nanoseconds only for executing a single step in a program. Okay, a program consists of many lines or many subprograms or anything. So in processing each step or each line of a program, it takes only few nanoseconds. But the cycle time that corresponding to a neural event because of the external stimulus takes place in milliseconds range. Okay, but because of this, computer processes information a million times faster. Because of the supercomputers that we have, so the processing of information is very, very quick. So when comparing to that of the human brains, the computers process things in a faster way. In processing, so neural networks, these neural networks are the biological neural networks. So this biological neural network can perform massively parallel operations. It is performing more than one task simultaneously. So most of the programs have number of instructions and they operate in a sequence. So only in a sequence the programs has to be executed by one instruction over the another in a conventional computer. But in our human brain it is not so. So a program has to be executed in a sequential manner only. If I am going to skip a instruction or a subprogram, then my result will be wrong. But the brain operates with massively parallel operations. The brain performs multitasking. So more than one task it is going to carry out with fewer steps. With the fewer steps. So the processing of the brain neural networks is higher than that of the artificial neural networks. So because of this massive multitasking operations, superior performance of human information processing for certain tasks is higher. Then we compare the size and complexity. So the biological neural network have a larger amount of computing elements, and it is not only with the neurons. That is, the computing is not restricted to within the neurons. So the number of neurons approximately that is available in brain is 10 to the power of 11. So 10 into 10 into, so 11 tens. You have to multiply, and that much amount of neurons is available in our human brain. And the total number of interconnections, the total number of interconnections that is available between these neurons is roughly around 10 to the power of 15. So this much amount of elements are present in the human brain, so which is very, very useful in processing of data. So the size and complexity of connections. So the connections or the interconnections that exist between the neurons is very, very complex, and also the size is very, very less. So this gives the brain the superpower for performing complex tasks that cannot be carried out on a computer. So because of the size and the complexity of connections that exist between the neurons, the brain has the superpower in performing complex tasks which cannot be carried out by a computer. So the brain, the complexity of brain in computing the complex task not only takes place inside the cell body or soma, that is the nucleus. Okay, the cell body or soma, but also in the dendrites and synapse. Dendrites are the information nodes, where synapses connects one neuron with the another neuron, and that is the small gap through which these neurotransmitters will get connected. Then storage. So the neural network strength is its interconnections. How the neurons are getting interconnected with each other. In a system or in a computer, the information will be stored in a memory. Either it may be external memory or it may be an internal memory, and each and every location is given their address. A memory address will be provided. A new information that is being stored in the memory of a computer in its previous location will erase the previous data. I am going to provide a memory location to a new information. I am receiving a new information, and that information I am going to store. If I am going to provide a memory location, if there is any previous data in that location, that will be replaced by the new information. But in the case of neural network, the information will be added by adjusting the interconnection strength without eliminating or destroying the old information. So 10 years back or 20 years back, what has happened to us? Still we can remember. And because of this interconnection strength among the neurons. That is, the old data will not be eliminated or will not be altered because of storing the new informations. So the information that is available in the brain is adaptable. Okay, whereas in the system it is strictly replaceable. Once we are going to move over the memory, for example, if I am going to have a specific memory only, for example, 1 GB or 2 GB, for example, if the memory level exceeds that, then these old memories or old data has to be replaced with the new informations, or I have to replace that memory to a higher level, for example 1 TB, 2 TB, likewise. So whether I have to increase the memory capacity or the old information has to be replaced with the new information. And fault tolerance. So the tolerance to fault is higher in the case of biological neurons because the information is distributed through the interconnections. Even when few connections are snapped or few connections are not functioning because of illness, for example, some of the interconnections are not going to function properly, the information will be still preserved. The information will be still preserved because of the distributed nature of the information in the biological neurons. But the computers are not tolerant to faults. If the memory is corrupted, obviously the performance of the computers will be outdated. So the memory gets corrupted, then obviously the system performance will get down. The control mechanism. So there is no central control for processing the informations, but because in each and every neurons, the nucleus acts as the central processing unit. So it is a distributed system. There is no central control mechanism since each and every neurons is a central processing unit. But in the case of a system, it has a central processing unit, okay, which monitors the activities of the computing. But in the case of neural networks, the neurons acts as the central processing unit where it acts based on the information that is available locally and transmit it to the next neurons. So there is no specific control mechanism in the case of biological neurons. Now coming on to the history of neural networks, the artificial neural networks. So it starts in the year 1943 by McCullough and Pitts. They developed the first mathematical model of a single neuron. They developed the first mathematical model of a single neuron. This model has been modified. Okay. Subsequently, the single neurons we are going to make it into 2, 3. Okay, likewise, and it is widely applied in the subsequent applications. Next, in the year 1949, Hepps modifies the connection weights, the weightages that we are going to provide for each of the inputs. Okay, he modifies the connection weights. They examine whether two connector nodes are simultaneously on and off. The weight varies depending upon the condition of the connector nodes. So, Hepser modified the connection weights. And in the year 1958, Rosenblatt's perceptron neuron model, perceptron neuron model and learning rules based on gradient descent methods, has emerged. So from there only we are going to move to this stage. There are many further modifications and developments in the ANN, but these three are the initial stages of development of ANN. Now, what are neural nets? So from this we are going to speak only about the artificial neural networks. So this neural network, or generally call it as neural nets, is an artificial representation of human brain that tries to stimulate, it only tries, tries to simulate its learning process. So exactly we cannot study or simulate, so we try to simulate this learning process. So animals normally react adaptively, that is, it changes dynamically to the changes in the external and internal environment to perform tasks. The term artificial means the neural nets are implemented in the computer programs. Because during the learning process, we require large number of calculations. So these neural nets are implemented in the computer programs that are able to handle large number of necessary calculations during the learning process, because in ANN we are going to just stimulate the learning process. So how we are going to learn from the environment? As a human, how we are going to learn from the environment and how we are going to behave, or how we are going to predict things. How we are going to predict things. If some vehicle is approaching fast towards us, so we think, we learn and we predict, so it is going to collide with us. So I have to move away from that. So this is the instant learning, or adapting to the situations. Similarly, by using these neural networks, I am going to learn the process of the human brains. So this is how we are going to combine things. So here you can see the first is a single model, and the second one is the multi-level models. So x1, x2, x3 are my inputs. F of x is my function value. F of x is my function value and y is my output. The function value is nothing but how these inputs are getting converted into a output based on some activation functions and weightages that is provided, based on the activation functions and weightages that is provided. The below figures, figure number D, it consists of multiple perceptron models in which we are going to have an input x1, x2, x3 and three outputs we are going to have. So the interconnectivity will be higher. So in the previous case B, we have three inputs and we are going to consider one output. But here we are going to consider three outputs. In between them we have hidden layers. We call it as the hidden layers, that is connected by means of the synapse. The synapse is the gap that is provided between the two subsequent neurons through which the neurotransmitters will merge. Thereby the information will be passed. So what are the various terminologies that we use between the biological neural network and the artificial neural network? In the case of neuron, we call it as the node. In the artificial neural network, we call it as the node. Input node, output node, or hidden nodes. Synapse, it is nothing but the connections that exists between the inputs and the hidden layers, or between the hidden layers to the outputs, how they are getting connected. So synaptic efficiency, the how efficient the synapse is. So it decides upon the connection strength or the weightages that we are going to provide. So depending upon the weightage, the strength gets increases. The firing frequency. What is this firing frequency? Because in biological neurons, we are going to deal with the electrical impulse. So we are going to use the term firing frequencies, and here we are going to call it as the output of the node. So these artificial neurons look similar to that of the biological neurons, and it works in the same manner as for biological neurons, neural system. So artificial neurons are similar to that of the biological neurons, and the function is the same. So the information, that is the inputs, is sent to the neurons based on the incoming weightages. So what weightages that we are going to provide? What weightages that we are going to provide? So based on that, the information will be sent to the neurons. So here we can see x1, x2, x3 and xn are the various inputs. So the weightages that is given to the inputs are W1 for x1, W2 for x2, W3 for x3 and W4 for xn. Then we are going to add, then we are going to sum all these inputs based on their weightages, and then we are going to have the activation function, and based upon that only we are going to have the output. So the weightages and the selection of appropriate activation functions improves the efficiency of the ANN. So that is very, very important. And apart from this, the type of model that we are going to select, whether we are going with single layer or multiple layers, whether we are going with the feed forward or feed forward back propagation, there are many models or architectures. So which activation function that we are going to use and what type of model or architecture that we are going to use determines the efficiency of the ANN or effectiveness of the ANN. So the input is processed by a propagation function that adds all the weight values of the incoming weights. So the input is processed by a propagation function or a activation function based upon the input weights that we are going to give it for each and every variable. Then we will be having a value from the propagation function. We will be having a value, and that value will be compared with a threshold value. The threshold value is a reference value. The threshold value is a reference value that can be a maximum or that can be a minimum. In the case of biological neurons, when the simulations are higher than that of the threshold value, then only the information will be passed to the subsequent neurons. When the stimulation is lower than the threshold value, the information will be inhibited or the neurons will be inhibited. So neurons will be activated when the stimulation value is higher than the threshold value. Similarly, here in this case, so the resulting value of this propagation function is compared with the certain threshold value based on the neurons activation function. Based on the neurons activation function that we have selected. If the input exceeds the threshold value, then it will be activated, otherwise it will be inhibited, as similar to that of the biological neurons. So if activated, that is, if my input or the resulting value of inputs is higher than that of the threshold value, then it is activated. In this case, the neurons send an output to the next connected neurons with the outgoing weight. If activated, the present neuron will send an output based on the weightages to the connected neurons or to the next level neurons. And similarly, it will go. For example, from input neurons to hidden layers, then from hidden layer to the output layer. So subsequently, it will be moving. So the output, that is the signal that the neurons transmit. The output is nothing but the signals that the neuron transmit is determined by applying the activation function. The activation function is also known as transfer function. Okay, to the weighted sum of the inputs. So, what is the weight that we are going to have or consider for the input parameters will have an effect on this. Okay, the output depends mainly on the activation function or the transfer function that we have to select. Okay, so these functions have a dynamic range between -1 to 1 or between zeros to 1. Okay, these activation functions have a dynamic range of values between -1 to +1 or between zeros to 1s. There are many activation functions: linear, sigmoidal, piecewise, like this, stepwise, ramp. There are many activation functions. So these activation functions differ in terms of complexity and outputs. If I'm going to improve the complexity or increase the complexity, then accurate outputs can be obtained. If I am going to select a simple activation function, then I will also get a nearby output, but that will not be as precise as that of the others. So a comparison can be made between different activation functions. So what are the assumptions made in this artificial neural network? The position of the neurons node of the incoming connection is irrelevant. The first assumption that I am going to make is the position on the neuron, that is the node of the incoming information or connection, is irrelevant. So whatever the position of the neurons, it doesn't have any relation at all. So each node has a single output value. So each node produces a single output and it is getting distributed or connected to other nodes via outgoing links. For example, I am going to have two input variables x1, x2, that is going to predict an output y. So x1, x2 my input variable and I am going to predict the output y. In the hidden layer, I am going to have three neurons. So x1 will be connected to all these three neurons of the hidden layer, and similarly x2 variable will be connected, that is the input neuron x2 will be connected to the three neurons or nodes of the hidden layer. Similarly, these three hidden layer neurons will get connected to the single output. So each node has a single output function and that is distributed to other nodes through their outgoing links, irrespective to their positions, wherever their positions are, but it is getting interconnected with each other. So here in this, all inputs come at the same time. If I am going to consider a neurons, in the case of a hidden layer, if I am going to consider two inputs, so I am going to have inputs coming from both the neurons at the same time. So it remains activated at the same level so that computation has to take place. So all the outputs will come at the same time to a particular neurons. Okay, and at the same time, it should be ready for computations. So in this case, an alternate is to postulate the existence of buffers. Okay, the buffer is nothing but a temporary memory. The buffer is nothing but a temporary memory to store the weightage that we are going to provide to the inputs. So based on that inputs only we are going to analyze, or we are going to have the values, the propagation function values. So these weights will be kept. So these values will be kept in the buffers and subsequently it can be used. Then we move on to the activation functions. So the activation functions it is a method of processing the neural networks. So activation functions are nothing but that provides the output based on the propagation function values depending upon the weightages that is provided. So the output mainly depends upon this activation function, or in other terms, the method of processing of neural networks is mainly achieved or determined by means of these activation functions. So this activation function is nothing but a mathematical function. It is a simple mathematical function that converts the input to an output. Along with that, it adds the effectiveness and the efficiency of the neural network processing. So here we are going to involve the mathematical function. Apart from this, the effectiveness and the efficiency of the neural networks is incorporated in this activation functions. That's why what type of activation function that we are going to select, it will have an impact on the determined output value. So without these activation functions, the neural networks is similar to that of a linear function. If I am not going to consider any activation functions, then neural network is nothing but a linear function. So these activation functions only make this as a neural network. So what is a linear function? So the output is directly proportional to the input. So here we are not going to predict anything. A mathematical model will be there. So based on the mathematical model, if I am going to give some specific inputs, the output will change proportionately. Like a regression equation, like a regression models. But here in this case of this activation functions, so prediction, how a neural network works in our brain. So the similar thing will be incorporated into the system. For example, a linear function y is equal to 2x plus 1. So this 2x plus 1 is a function of x. Okay, depending upon the value of x, y changes. So y is directly proportional to the value of x. So this is an example for linear functions. So when this is given to the activation functions, then the output is to change or changes in an adaptive manner. First activation function that we are going to see is the step function. So once we are going to fix the threshold value, because a neuron gets activated or inhibited depending upon the threshold value. When the value of the input neurons or this specific neuron is higher than that of the threshold value, then only it will get activated. When the value is lower than the threshold value, then the neurons get inhibited. Okay. So once we fix the threshold value of x, for example, x is equal to 10, then the function will return 0. Or if the mathematical sum of the inputs is above or below the threshold value. Okay, so depending upon that, this will get activated out. So this is the representation of the step function. So this varies between -1 to +1. So only when it has the threshold value, that is -1 or +1, then only it will have start working. Then we have the second one, the linear combination. So instead of managing a threshold value, the weighted sum of the input values is subtracted from the default value. So I am going to have consider a value. The weighted sum of the input values will be subtracted from the default value. Then we will have a binary outcome that may be positive or negative. That may be positive or negative depending upon the output of the subtraction process. So the weighted sum of the inputs will be getting subtracted from the default value. Okay, based on the training functions. So this is how the linear combination is there. Then comes the sigmoidal. So this sigmoidal is a curve with extent. So here we can see this. So this is a curve with an S-tail. So this is a special case. This is a special case. In the first image, you can see the function, a sigmoidal curve varies in between zeros to 1. But here in the second case, it varies between -1 to +1. So depending upon in which values this is going to work, it have different names. Then we have the piecewise linear function. So this piecewise linear function is a combination of various linear functions. So how we are going to select these different functions? So this piecewise is a combination, okay, or a collectiveness of different linear functions. So the choice of the linear function depends on the relevant region of the input space. So in this case, we can see there is a sigmoidal one in which I am going to convert that into dotted lines. You can see a linear one. So 3 linears we are going to have here. So step and ramp functions are special cases of the piecewise functions. Okay. So in these cases, the second derivative should be equal to 0. Okay. So in this case, the second derivative that we are going to consider should be equal to 0 wherever it exists. So the advantage of this piecewise linear function is they are easily to compute rather than the sigmoidal value. So here in this image, you can see the sigmoidal function that changes between the values of -1 to +1 is converted into piecewise linear functions. By making this, it is very easy to compute than that of the sigmoidal functions. Then we have the Gaussian functions. So Gaussian, we know it is a bell-shaped function. Okay, it is a bell-shaped function. So these are continuous in nature. So these Gaussian functions has a single maximum. Okay, and it has a larger magnitudes of networks. So you can see, depending upon the limits, depending upon the lower and the upper limits, the magnitude gets to change. So we have seen different activation functions. So choosing the proper activation function is the key thing to make the network perform at its best and to have good training. So we have training, testing. Okay, during the testing we are going to predict. During the training I am going to have both input and the output, that is called a supervised training. That and all these things we'll see later on. Okay, So the amount of prediction or training depends mainly on the activation function that we are going to select. So there is no thumb rule in selecting what type of activation function that we have to select. So the selection of activation functions depends on your data and in which form you want the data to be transformed. Whether we have to transform that in a linear manner or we have to transform that into a sigmoidal function likewise, or in a step function we require. So what is your data and how the data has to be transformed? Okay, based on that only we have to select the activation function. So if you are going to choose, if you want to choose a particular activation function, then we have to study the graph of the particular function and we have to see how the result changes with respect to the input values. So while doing this ANN, we have to select different activation functions, then we can make a comparison out of that, and the best transfer function or activation function that is suitable for our work should be selected. Because for my data, the linear is best or the stepwise will be a best, but for your data sigmoidal will be best. So it depends on the data that we are having and what is the and how we are going to transform the data. So in artificial neurons, the neurons are grouped in layers. The neurons are grouped in layers. For example, the input neurons are grouped as input layer and the output neurons are grouped in layers that is called as output layers. So generally these neurons are grouped in layers that is called as neuron layers. So each neuron in one layer is connected to all neurons of the preceding or the following layers. For example, if I am going to have 3 input variables in an input layer and simultaneously I am going to have 3 output neurons. So 3 input neurons, 3 output neurons. X1, X2, X3. Similarly Y1, Y2, Y3. So X1 should be connected with Y1, Y2, Y3. Similarly, X2 should be connected to Y1, Y2, Y3 and the X3 should be connected to Y1, Y2, Y3. That is, each and every neurons in the layer should be connected to the subsequent layer to all the neurons present. So the subsequent neuron to input is the output neuron layer in which we are going to have 3 neurons. So each neurons in the input layer is connected to the all the neurons in the output layer. So the information in the neural net passes layer by layer. Okay, the layer by layer is input layer to output layer. Before that output layer, if I am going to consider a hidden layer, then the information will be passed from the input layer to the hidden layer and from the hidden layer to the output layer. So layer by layer, the information will be propagated. So here you can see the input layers, the input neuron layers, weight matrix, then hidden layers, then weight matrix, the output neurons are the output values. So each neuron in the input neuron layer, so 3 input values I am going to consider. So 3 neurons I am going to consider in the input layer. So each input is connected to the 2 neurons of the hidden layer. In the hidden layer I have 2 neurons. So all the 3 input neurons are connected to the 2 neurons. Similarly, the hidden neuron is connected to the two outputs. So each hidden neuron is connected to the two output neurons. Thereby, the output we are going to obtain. So the value of output that we are going to obtain mainly determines on the weight matrix that we are going to consider, and also the activation function that we are going to select. So basic structure of an ANN. So that is the topological structure. So here we are going to consider two layers with M and N processing units. Processing units are nothing but the neurons. So in F1 layer I have M neurons, and in the F2 layer I have N neurons. So now I am going to provide connections to the jth unit in the F2 layers from all the units of F1. That is, I am going to consider a neuron in the F2 layer. So I am having two layers, F1, F2. In F2 layer, I am going to consider a neuron. So that neuron will be connected from all the input layer neurons. Okay. So based on the connections, we are going to have two topologies, that is in star and out star. So that is like a fan in and fan out geometry. So in star and out star. So during the learning process, the normalized weight matrix approaches the normal input vector in the F1 layer. Okay, during the normalized weight vector, okay, the in star approaches the normalized input vector at the F1 layer. So here you can see that I am going to have two layers, F1 and F2. I have M neurons in F1 and N neurons in F2. So each and every neurons in the F1 layer is connected to the jth layer. Okay, depending upon the weightage and weight vectors, we are going to get it connected. So the activation vector, okay, activation weight vector of the jth unit, because we are going to consider only j here. That's why we are going to call it as the jth unit or the jth neuron in the F2 layer will approach maximum during learning. Okay, it depends upon the activation weight we are going to consider. Okay, so thus the operation of an install can be viewed as content addressing the memory. So when the content is addressing the memory, then it is called as install. Okay, if the memory is addressing the content, then it is called as outstar. That's the difference. So in the case of outstar, okay, we are going to have the memories addressing the content. Here you can see that. Second one, we can see all the jth neuron in the layer F2 is getting connected to all the neurons of the F1 layer. That is, the memory of J is addressing the contents that is available in each and every neurons of F2. So now you can see now. In the case of an outstar, during learning process, so during the learning process, the weight vector connections from the jth unit in F2 approaches the F1. Okay, whenever there is an input neuron in the F1. Okay, so this produces the activity pattern. This produces this activity persons that corresponds to an input vector A, although the input is absent. So this is seen as a memory addressing the contents. As in the case of instar, the contents will be addressing the memory from content to memory, but in the case of outstar, memory to content. That is the flow of data. So this is other. So in the previous case, we have considered only the jth neuron. We have considered only the jth neuron, and the other neurons up to N will not be considered in the F2 layer. But here in this case, you can see each and every neuron is being interconnected, whether it may be a in star or it may be a out star. For example, look at the first neuron in F1 layer. That first neuron is connected to the first neuron in F2, then second neuron in F2, and jth neuron in F2, and the nth neuron in F2. Similarly, to IM. So all these things are interconnected. So because this only perfect learning is possible with the models. So this we have the bidirectional associative memory. So the contents can read the memory, at the same time the memory can read the constraint. That is both in star and out star. We call it as the bidirectional. Similarly, auto associative memory. So we are going to consider parallel. Then we come across the different types of learnings. One is called as the supervised learning and the other one is the unsupervised learning. The learning algorithm of the neural network, the learning algorithm of the neural network that we consider normally is maybe a supervised or an unsupervised learning. Supervised, there will be a supervisor. Unsupervised, there will not be anyone to supervise. That is, if my output is known, then it is called as a supervised. So my supervised is the output. I have an input and I have an output. So based on the combination of inputs, I have to train based on the output. So here the output values that we are going to provide is going to supervise the learning process. Is going to supervise the learning process. That's why it is called as a supervised learning. So a neural net is said to be learned supervised if the desired output is already known. So response of the network to the inputs is measured. So what is the predicted output that we are going to measure from the system or from the neural network? So automatically the weights can be adjusted in order to reduce the difference between the actual and the desired output. The actual output is maybe an experimental output. For example, experimentally I have some outputs and that I am going to give it as a supervised output. Now the system, the neural network is going to predict the output and that predicted output should be nearer to the actual output. How this is possible? The weightages that we are going to provide to the inputs has to be modified. The weightages that we are going to provide to the inputs should be modified in a way that the difference between the actual and the predicted or the desired output should be lower. Then unsupervised. So unsupervised is there will not be any specific outputs. So no such target options or the target outputs. So only we are going to provide the inputs. And the weightages will be considered by the system itself. So the neural network adjusts its own weights depending upon the similar inputs produces similar outputs. So for this, higher number of data is required. If I am going with unsupervised, then higher number of data is required since I am not going to provide any target output. So the weightages will be adjusted by itself so that similar inputs will result in similar outputs. That is the combination of inputs. Okay, if I am going to have the same combination of inputs, then the same output should be provided. So for this, the weightages of the input should be adjusted by the system itself. So without any external assistance, in the case of supervised algorithm, we have an assistance. So what is that assistance? The assistance is nothing but from the output values that we are going to provide or the target values that we are going to provide. But in the case of this unsupervised learning, there will not be any output, that there will not be any external assistance, but the network itself will identify the pattern and differences. The network itself will identify the pattern and differences in the inputs. So how the combination of input varies. So what will have, it will have an impact on the predicted outputs. So what are the different types of AL that normally we have? So normally several types of neural nets exist, but they are classified under their type. What is the type of AL? Whether it is a feed forward or feed backwards. So feed backwards is a better algorithm. Feed forward and then feed back propagations. So for weight adjustments, I am going to have to provide the output fed once again so that the desired output can be obtained. Based on their structures, single perceptron model, multi-layer perceptron models, the learning algorithm that we are going to use, whether they are supervised or whether they are unsupervised. So their type, feed forward or feedback. Feedback propagation methods likewise. The structures, whether it is a single perceptron model or multi-level perceptron models, MLPs, we call it as multi-level perceptron models. Then we have the type based on the learning algorithm that we are going to use, whether we are going with the supervised learning or unsupervised learning. Perceptron model. So a perceptron is nothing but a single neuron. So that classifies a set of inputs into one of the two categories, either 1 or 0 or 1 or -1. Okay, so a perceptron is nothing but a single neuron models. So this perceptron uses a step function that it ranges between -1 to +1. So that is the step function in activation function. The activation function that these perceptrons are going to consider is step function. So it returns 1 if the weighted sum of the input exceeds a threshold value, or 0 when it is not going to exceed the threshold value. So if the value is higher than the threshold, then when I will have 1. If it is not so, then 0 will be my value. So when more than one perceptron model is combined, so or when layers of perceptron are combined together, they form a multi-layer architecture. So this multi-layered architecture will provide us the complexity that the neural network processing should have. So here we are going to process only complex data, or we are going to predict data that a complexity exists. So for this, the single layer or single layer perceptrons model does not provide any fruitful results. So in order to increase the complexity of the developed model, we have to go with this multi-layer architecture. You have to go with this multi-layer architecture. So rather than this single layer or single neuron perceptron models, generally we'll be focusing more on this MLPs, that is multi-layer perceptron models, because it is the widely accepted neural network model, because the performance of these MLPs is very good. So exact prediction of outputs for a given set of inputs is possible with this multi-layer perceptron models. What is a perceptron model? Here we can see an input layer and an output layer. Okay, so this is called as a single layer perceptron. Only one layer, one input layer, one output layer. There is no hidden layer at all. So in the input layer, we have 3 input values, x1, x2, x3, that is connected, or that is made to predict 2 outputs, y1 and y2. You can see all the neurons in the input layer is connected to the 2 outputs. So x1 is connected to y1 and y2, x2 is connected to y1 and y2, and x3 is connected to y1 and y2. And also we are going to have the weight matrix. The weight matrix adjusts itself or it adapts or it changes dynamically so that a perfect output can be obtained for similar input conditions. Then we have the multi-layer perceptor models, that is MLP. In the MLP, more than one input and output, it is called as multi-layer. That is, here we are going to add a hidden layer. If the complexity of the system is higher, then we have to include the hidden layer. The number of layers or number of neurons in the hidden layers can be varied also. So here in this example, we have considered only two neurons in hidden layers, but that can also be improved or increased. In this multi-layer perceptron model, we have considered only one hidden layer. We can also consider two hidden layers, three hidden layers, and somewhat like that. But with the higher hidden layers, the computational time will get increased out and the complexity of the process will be higher, but accurate prediction is possible. For example, with one hidden layer, if I'm going to solve or predict the outputs for a given input combination is 1 minute, then obviously with two hidden layers, it will be around 1.5 minutes. For example, I am telling. So the computational time tends to increase. Forward propagation. So previously itself we have seen from input layer, the data will get transformed to the subsequent layers. From one layer to another, the data will get or the informations in the data will get transferred. So in the case of multi-layer perceptron models, the processing of data from one layer to from the inner layer to hidden layer will be taking place, and from the hidden layer it will be subsequently delivered to the output layer, and this is called as feed forward propagation. Forward, input hidden and then output, no backwise. I am not going to feed it from backwards. So it is called as feed forward. Forward only I am going to move. So the sum, that is input variable value into weightages plus bias. That is, the sum is nothing but individual weightages of variable into value of the variable or variable value plus some bias values should be considered, is applied at each value, and then the activation function value is propagated through the or transported to the next layer. For example, from input to output. Then once again I have to include a activation function, because from hidden layer to output, once again I have to provide some weight, and once again I have to have a activation function. So in the previous condition you can see there will be two weight matrix. For multi-layer perceptron, we have two weight matrix. But in the case of single layer perceptron, we have only one weight matrix. In the single layer perceptron, the sum is nothing but weight into input layer weight plus the bias. That is fed to the activation function. Here in this case, the weight matrix 1, the sum is equal to the weight into the input value plus bias, that will be fed to the activation function, and that activation function will provide a value to the hidden layer. Similarly, the hidden layer neurons will have an input, so that is the input value. Now the weight matrix 2 considers the sum, that is the value of hidden layer neurons into the weightages plus bias, that is fed into the activation function, and finally we will have the output layer values. So this complexity increases subsequent layers. Then from the hidden layers, we are going to provide the transfer the information to the output layers. When more amount of hidden layers are used, then it may give rise to deep neural networks. That is deep neural networks. With this, a perfect or precise prediction is possible. So these models are called as feed forward because information flows through the function being evaluated from X through the intermediate computations, that is hidden layer, and finally to output Y. Since there is no back propagation, I am not going to have a back propagated value, or these feed for propagations are like a open loop system. Will not be considering any feedback. Okay, so this forward propagation is similar to that of a open loop system. So in this feed propagation, as told, there are no feedback connections. That is, no output of the models are fed back to itself for adjustments or for dynamic corrections. Okay, if I am going to feedback the outputs, then the system itself will adjust so that a desired output can be obtained. For example, take a air conditioning room. I am going to set my temperature as 22 degrees centigrade. Okay, it adjusted or the compressor runs until 22 degree reaches. Then it switches off. If it is getting switched off, then obviously the temperature may rise. But in the case of closed loop system, I am going to measure the temperature, the room temperature, that is the existing room temperature. If the room temperature changes, then subsequently the compressor has to start again, so that the 22 degree, the desired output should be maintained. So this is the feed forward propagation neural network model. So here we can have three layers. Three layers. The first hidden layer or the input layer, the hidden layer 1, hidden layer 2, and the output layer. Okay, we are going to initially provide the weightages to the inputs. We are going to have, that is first hidden layer is nothing but the input layer itself. Okay, that which we are going to provide values. So here we have 4 neurons in the input values. Okay, then we have hidden layers 1, 2, 3, 4 and N2. So how to frame this number of neurons in the hidden layer? That itself is a great task for us to decide how many neurons that we have to select in the hidden layer. Then subsequently we have the output layers which produces the outputs. So here we have x1, x2, x3, xn. That is, for example, 4 inputs, and here we have 3 inputs, y1, y2 and ym. So there is no feedback system that is incorporated in this. Then we have feed forward back propagation. It is not just back propagation, it is feed forward, but at the same time we are going to back propagate the output values to the system so that exact or the desired value that is closer to the actual value can be obtained. So in this we are going to incorporate the back propagation algorithm. In this we are going to incorporate the back propagation learning algorithm. So here you can see the dashed lines with the arrow mark, feedbacks. So here we have 3 inputs in the input layer, then weight matrix 1, then hidden layer we are going to have 2 neurons, then weight matrix 2, then we have the output layer, then the outputs. The output layer values will be fed back to the hidden layers. So a comparison will be there. That is, a back propagation learning algorithm will be there. Then the values of the hidden layer neurons will be fed back to the input layers. So similarly, the values will be fed back so that a closed loop system will be formulated so that the desired outputs can be predicted. But with this, the complexity of the problem of the network gets increased. A commonly supervised learning algorithm. Why we call it as the supervised? Because we are going to provide the output target value. During training process, I am going to provide a target value. That is my experimental output. Since I am going to provide the output, it is called as supervised learning algorithm. If I am not going to provide that, then it is the unsupervised. But in this case, this back propagation algorithm works fine only with the supervised learning algorithm. So here you can see the input layer, the output layer, and the two hidden layers. We have two hidden layers here. So the number of neurons in the input layer is 3, whereas the number of neurons in the output layer is 2. Here you can see in the output layer we have a dot with the green, that is the difference in value. Okay, the difference between the actual experimental value and the values that is given by the network model. So by making the comparison, the difference in desired values can be obtained. That difference will once again be fed back to the system so that the weightages will be adjusted. Okay, the weightages will be adjusted in such a way that subsequently the difference will be reduced as much as possible. As much as possible. So how to see the difference is very less. Here we can have the regression coefficient value R square. During the ANN, we'll have some plots, R square plots. That is R plots. That is R is nothing but R or R square. It is called as the regression coefficient. If the regression coefficient is 100 or 100% or 1, then it is the ideal value. A value that is close to this is very good. Okay, so the difference in things. So the difference in things will be fed back to the subsequent layers. So here in this case, the red dots represents the feedback of data from the output layer to the subsequent hidden layer 2. So from there it will be transferred once again to hidden layer 1, and from there it has to be transferred to input value. So the weightages that I am going to provide will have to be adjusted in a precise manner so that perfect prediction is possible. So what is the procedure in performing this back propagation algorithm? So initialize the network with the random weights. So first I am going to consider random weights and I am going to initiate the network. So for initially itself I doesn't know what weight to be provided. So the system itself will provide the weights. So in the subsequent steps, first of all I have to train the model. Okay, I have to train the model. So forward pass. So forward propagations. So it calculates the network's error. So how much error that is produced between the desired output and the actual output. So that is this case, that green. How much difference exists between the actual and the predicted outputs. Okay. Now, when the difference is high enough, then I have to back propagate it, or I have to pass it backwards, layer by layer. Here also I have to do layer by layer. In the forward pass from inner layer to out to hidden layer and then to the outer layer. Similarly, in back propagation, we have to start with the outer layer that has to be given to the inner layer, and once again I have to give it back to the input layer. So for all layers, I have to backpass these values. then we know what is the error function that arises because of the difference between the experimental value and the predicted value. Now I am going to change the weights. So that is the adaptive or dynamic change or adapts dynamically. Okay, so now the weights are being changed. In the initial condition, during initialization, you are going to randomly select the weightages. You are going to randomly select the weightages. But depending upon the back propagation, is the error function that we are obtaining, the weightages has to be adjusted automatically or dynamically, so that at the final the error function has to be reduced or minimized. We cannot eliminate, but we can minimize it as low as possible. So here comes the methods that we are normally using in this. We are going with the gradient descent method. We are going with the gradient descent method. So it is an iterative approach for error calculations. We call it as GDM, gradient descent method GDM. So learn GDM and train GDM. Training the network model using the gradient descent method and learning the model or the learning the relationship using the gradient descent method. So train GDM and learn GDM. So this gradient descent method is an iterative approach that is specifically useful in reducing the errors in any learning models. So in the back propagation, what we are going to actually do is we are going to adjust the weights so that the difference between the actual and the predicted values will be as low as possible. So the process of iterating the update of weightages and bias with the error, okay, with the activation function is the gradient descent approach. Right? The purpose of back propagation is to eliminate error or it is to correct the error. Okay, this is carried out by varying or by updating the weights along with the bias, because the sum is equal to input into weight plus bias. So input values I cannot change. I can change only the weightages and then I can change only the bias. So for each and every iterations, I have to update the weight and bias with the error time derivatives of the activation function, and that is called as the gradient descent approach. So the steepest descent step size. Descent is reduction and ascent is increasing. The steepest descent is rapidly reducing and steepest ascent is rapidly increasing. Right? So steepest descent step size is replaced by a similar size from the previous size. So previous step or iteration process, we have a weightage, and depending upon the steepest ascent or steepest descent, that weightages will be updated, but based on the previous iteration or previous step. So what this gradient actually means? This gradient is nothing but the slope. The gradient is nothing but the slope value of the curve, and it is the derivative of the activation function. So what is the activation function that we are going to select? Whether we are going with the stepwise or linear or sigmoidal functions, okay, or Gaussian functions. So this gradient will be the slope of the particular curve, and it is the derivative of the activation function. So since there is no thumb rule in selecting the activation functions, so initially consider what are the available activation functions and select from this which is the best activation function that is required for your specific work. So the objective of deriving the gradient descent method is to identify the minimum global cost. The minimum global cost is associated with the minimum error. Okay, is the minimum error that we are going to obtain. So when the error is low, then obviously the model will fit better and the predictions are more accurate. So that is the procedure of this gradient descent method. That is, we are going to reduce the error. Okay, by reducing the error, a perfect fit can be obtained. So when the error gets decreased out, the R square value will be higher. That is, a perfect model fit can be obtained. If a perfect model is fitted, then accurate prediction is possible. So that's what we are going to conclude in this. So here you can see the gradient is nothing but the slope. So whether it is the G plus or G minus. Okay, G minus is the negative slope and G plus is positive slope. Okay, so my ultimate aim is to reduce the error. Okay, the initial weight I am going to randomly I am going to select the weightages, and by each and every iteration process I am going to move towards the global minimum cost where the error will be lower. So that is the purpose of this. So what are the steps in gradient descent method? Randomly choose the initial values, compute the gradient, that is the slope, with respect to each parameter of the model, change the model's parameters, and then move in the direction of decreasing error. So here you can see, I will start with the initial weight. So see the cursor moving, I will start with the initial weight and I am going to move downwards so that I am going to reduce the error. So randomly choose initial values, that is weightages, then compute the gradient, then I am going to compute the slope, then I am going to change the model parameters, and then I am going to move in the direction of global minimum cost, that is reducing the error percentage, and then we are going to repeat these two steps until G approaches 0. The G may be -1 or +1, but our ultimate aim is to move towards G is equal to 0, that is 0 slope. That is, no difference exists between the actual and the predicted values. Then we come across two words, that is learning rate and momentum coefficient in ANN. The learning rate is a common parameter which affects the speed at which ANN arrives at the minimal solution. So how much speed the ANN is going to arrive at the solution, that depends on the learning rate. So the momentum parameter is used to prevent the system from converging to a local minimum or saddle point. The saddle point is a min-max point. Okay, the global minimum and the local minimum. My error should be minimum. I am going with 100 iterations. For this first iteration, I am going to have some value. For the second, I am going to have another value. If I am going for 3, I am going to have another value. Among these 3 iterations, which is the lowest value? That is my global minimum. So for each iteration, I will be having a minimum value, and that is called as local minimum. Among the iterations that is performed, what is the lowest value? It may be from iteration 1 or iteration 2 or iteration 3, but whenever I am going to compare between 3 iterations, what is the lowest value? That is the global minimum. So it is this momentum parameter is used to prevent the system from converging it to a local minimum. Once a minimum is set, that itself will be accepting, even though the subsequent iteration produces a lower value than that, it will not accept that. So the converging it to a local minimum is a problem. So that should be eliminated. So by using this momentum parameter, we are going to prevent that. So high momentum parameter helps the system to speed up the convergence of the system, but can risk of overshooting the minimum. Okay, so we have to use a nominal momentum parameter. So a momentum coefficient or momentum parameter should not too low. Okay, because it cannot avoid local minimum. Okay, it should not be that much low or it should not be that much high, so that a moderate value of momentum parameter should be used. Then what is meant by epoch? One iteration is called as a epoch, right? So the one iteration, that is, the network is going to be provided with an input and the updating the network's weight. So one iteration, input to output. Okay, I will be randomly selecting my input to weight. So that is one iteration. So providing the network with a input and updating the network's weight. If I want to change, then I have to go for the next iteration or next epoch. So it is a full run. For example, if I am going to consider 100 iterations or 100 epochs or 10,000 or 5,000 epochs, then it is a full run for feed forward or back propagation for updating of weights. So it is also one full read throughout the entire data set. For example, if I am going to consider a back propagation, input, hidden layer, output. If I am going to consider back propagation, then output, hidden layer, input. So this is one iteration process. That is one epoch. So typically epochs that we are going to select should be thousands at a time, because whenever we are going to increase the number of iterations, then obviously the weightages will adjust itself, so that a perfect prediction model is possible. So don't go with 100, 200s. So we have to go with thousands, 5,000, 10,000. Likewise, we have to select. So weight and bias. So what is the weight? So weight, we are going to provide it to the input so that the output can be impacted. So this is similar to that of the slope in a regression equation, right? So the weight is multiplied with the input and added up with the bias to form the output. The weightages that we are going to consider should be multiplied or product into the input variable value, and then it is being summed up with the bias to form the output. So these weights are numerical parameters. These weights are numerical parameters that determine how strongly each neurons affects the other. For example, the input neurons, how it affects the value of the hidden layer neurons, how the hidden layer neurons affects the output layer neurons. So how strongly it affects, it is determined by the weightages. If I am going to have the inputs as x1, x2, x3, then the corresponding weightages will be w1, w2 and w3. So the output is a function of the input variable, that is nothing but the summation of the individual variable into its weightages plus bias. So we have to add the bias also. And what is bias? So the bias is nothing but an error term that we are, for a constant that we are going to add in a as an intercept in a linear equation. For example, y is equal to mx plus c. Okay, where x is the variable, input variable, m is the weightage and c is the bias. So the intercept, c is nothing but the intercept that we are going to add in a linear equation. Here the m is a slope. Similarly, the weight is nothing but a slope. So weight is nothing but a slope and the bias is nothing but an intercept, as in the case of a linear equation. So the bias is an additional parameter which adjusts the output along with the weights that we are being provided with the input variable. So the output is equal to sum of weights into inputs variables plus the total bias. So with this, we are closing this PPT, and here are some useful tips. As a thumb rule, we are going to use. So the number of neurons that we will be using in the hidden layer. So as I have told earlier, we have to fix the number of neurons in the hidden layer, but that can be fixed in a trial and error manner. Okay, first I will start with 2, then I will move on to 3, 4, 5, 6, 7, 8, 9, 10. I will go on. But at a certain number of neurons in the hidden layer, my output will be very close to that of that actual value. So that I am going to use. But as a thumb rule, the number of neurons in the hidden layer is calculated by the number of neurons in the hidden layer should be greater than or equal to 2 into number of input neurons plus 1. If I am going to consider 3 neurons in the input, that is, if I am going to consider 3 inputs, then 2 into 3 plus 1, so 7 neurons. The minimum number of hidden layer neurons should be 7. If I am going to consider 6, then a perfect model cannot be developed. So that is what it is. Okay. Similarly, if I am going with 4 input neurons, so 2 into 4, 8 plus 1, 9. So I should select a neuron that is minimum of 9, then 10, 11, 12 likewise. Here also we can straight away use the inputs and outputs, or we can normalize, If the output value is very high, then straight away we cannot use these values. Okay, this is particularly useful when we are going to predict more than one output. In these cases, we have to normalize these values. Using this formula. So normalized value is equal to 2 into actual value minus minimum value divided by maximum value minus minimum value minus 1. After predicting the output, that should be converted back into the original values or original sequence. For this, we have to denormalize these values. So normalized value plus 1, the maximum value. For example, if I am going to consider a tensile strength of 120 megapascal, okay, in an experiment, I am going to calculate the tensile strength. The maximum value may be 240 megapascal and the minimum is 80. So maximum value that we should enter in both the conditions, normalized and denormalized, is 240 and the minimum value is 80. So that I will have a perfect prediction. So initially go with the actual values. If I am unable to predict it correctly, if I am having some issues, so go with this normalizing values. If I am going to normalize, then obviously a perfect model can be developed. So what are the benefits of going for ANN? So these ANN are very flexible and adaptive in nature. This ANN acquires knowledge from their surroundings by adapting internal and external parameters. It adjusts its weights depending upon the supervised learning and back propagation algorithm. So adequate responses to unknown situations. Yeah, that also it is possible with this. That is, it adapts to the environment. Then flexibility. So these ANN have the flexibility to learn. That's why it is a subtopic of artificial intelligence that is used in the robots. So this artificial neural network model is based on the adaptive learning of machines. But there are some limitations. So even though whatever the biological neurons we are going to mimic, it is highly impossible to copy the true parallel tasking nature of the neural cells. Okay, because multiple tasking is possible with biological neurons, whereas we can do multiple tasking in these artificial neurons, but it is not that much close to the biological neurons. So the internal structure of biological neurons will tend to change or adapts to the environment, whereas the computer's internal structures cannot be changed. So the ANN results cannot be guaranteed. Okay, the ANN results cannot be guaranteed. If I am going to predict now, then if I have stored that model, that is possible. But once again, if I want to create a new model and if I have to train, then the values that we are going to obtain will be different in both these conditions. So what are the various applications of ANN? So pattern association and classifications, then regularity deductions, that is in components, then image processing, right? Most of the ANNs are used in image processing techniques, then robots, then speech analysis, okay, that is voice analysis. Then we come to the optimization problems for predicting the outputs, then robot steering, the movement of robots. So processing of inaccurate and incomplete inputs. We can do this because we can reduce this fuzziness in this also. Then quality assurance. So now we'll see an example, and in the afternoon class or afternoon session we'll have an hands-on training. So in this example I'm going to use a machining process that is called as wire cut EDM process. I'm going to predict the performance of this process and then I'm going to compare the results with the regression models. Okay, this is my input. I have considered 330 inputs. So I have performed the experiment with this 30 different combination of inputs. So I have selected 4 input parameters: gap voltage, pulse on time, pulse off time, then percentage reinforcement of percentage reinforcement. For this, I have performed the experiment and then I have determined and tabulated the outputs: curve width, surface toughness, and material removal. So here you can see the values are nearer to each other, 0.2, 0.75. These are very close. If I'm going to have another value that is in the 200 range or 300 range, then it is highly impossible to have closeness. So in that cases, go for normalizing of data. Since these values are nearly close to each other, no normalizing is required at this time. Then we are going to develop these layers. The input layer consists of 4 variables, that is gap voltage, pulse on time, pulse off time, and percentage reinforcement. And the outputs that we are going to predict is curve width, surface toughness, and metal removal rate. So in this, how many hidden layer neurons we are going to have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this, I have used the thumb rule. The minimum number of neurons should be greater than or equal to 2 into input neurons plus 1. So 2 into 4, here 4 input neurons. So 2 into 4, 8 plus 1, 9. So based on that aspects, I have fixed this hidden layer neurons. Then I am going to develop the ANN model and I am going to iterate it. During the iteration, I am going to have a plot like this. So that is the mean square error that we have used. So in the x-axis, we will come across the 10,000 epochs. The epochs are nothing but the iterations. Okay. So the dotted line is the best fit. The training is the blue. So you can see at the final, at the 10,000 epoch, everything is more or less constant. That is convergence. We have to look into the convergence here also. And also, the best fit should be as low as possible. That is the error. Mean sum to square should be as minimum as possible. Then comes the regression coefficients. During the training, so you can see the training or validation or test or all or. R stands for regression coefficient. Here you can have the equations. Okay, here we are having the equations. Output is equal to 1 into target plus 0.036. So similarly, we have equations for that. So the R stands for regression coefficient. The first one is 0.99, which is close to 1. Similarly, for validation, for test, and for combining all these three, training, validation, and test, we have the R value of 0. That is, a perfect fit is possible in this. Here you can see all the dots are nothing but the outputs. That is fitted to a model. So it is not even getting distributed on both sides of the straight line. It is fitted on the straight line itself. That's why I have obtained an R value of 0.99, which is close to 1. Then here we have the gradient. Okay, the gradient should be 0. Actually, it should be minimum. Okay, the gradient of the slope. Actually, at the final, that is at the 10,000 epoch, you can see the slope is very, very low. The slope is very, very low. So from this I can identify, then it is a best one. Then I am going to, first step in ANL is training, and second is testing. Okay, I am going to provide initially in the training session, I am going to provide input and the output. That is a supervised training I am going to provide. So after a perfect model is trained, how to check whether a perfect model is developed? From this R square value. So from this I can know now my model is fit. So now I am going to provide the testing. I have to test the model. So with these three values, okay, that is experiment number 5, 10, 15, 20, 25 and 30, I am going to provide the input variables. That is pulse on time, pulse off time, gap voltage and then percentage reinforcement. I am going to provide it as the input. What is the corresponding predicted value from the AN? That is given in the column number 5, 6, 7, AN prediction. I know the experimental outputs, I know the predicted outputs. Similarly, I have developed a regression equation. Okay, by using that regression equation, I am going to predict the outputs for the experiment number 5, 10, 15, 20 and 25 and 30. Now I am going to compare. The black is the experimental output and the red is the ANN output and the green is the regression output. So here you can see both the experimental and the ANN is fitting exactly. That is highly effective prediction is possible with the ANN. This is for output 1, this is for output 2 and this is for output 3. In all these cases, you can see that ANN outplays the regression equation. Okay, but the model that we are going to develop using this should be as perfect as possible. Apart from this, here you can see, so this is a graphical user interface that we can develop. Okay. In this, I am going to attach the developed model with this front end. We call this as the front end. So again and again, there is no need to give values for it. So I am going to develop a front end like this. So on the left side, I will have all the input control parameters. Okay, I am going to give the values for this. If I click predict, then my output responses will be predicted. How this is possible? So this is possible by developing a ANN model, okay, and then attaching this developed model with this front end, that is the graphical user interface. So that whatever values that we are going to provide here will be taken as input to the ANN, and if I am going to predict, then I am going to iterate the model and the output will be displayed here. Okay, this is also possible in MATLAB. Okay, so with this, I conclude my session now, and exactly at 2 o'clock, we will be having a hands-on training in artificial neural network in MATLAB environment. And thank you. And I will be coming to chat section. And if you have any doubts, you can get it clarified there. Thank you.